నమస్కారం. డాక్టర్ బిఆర్ అంబేద్కర్ సార్వత్రిక విశ్వవిద్యాలయ విద్యార్థులకు స్వాగతం. ఈ ప్రసారంలో
Hello students, we are going to discuss about a topic called band spectra. Band means a group of spectral lines originated from one type of action, something similar to rotation of a molecule about its center of gravity or vibration of atoms in the molecule about a equilibrium position. Next, the electronic movement of the electrons in the atoms of the molecule producing electronic spectra. So, like that we will have the energies associated with electronic, rotational and vibrational. All these things put together, total energy E is equal to E translational plus E electronic plus E vibrational plus E rotational. Hence, we will have quantization of electronic motion and quantization of vibratory motion and quantization of rotatory motion. Now, this electronic motion takes large amount of energy, hence the amount of the wave number associated is about 10 to the power of 6 centimeter minus 1, whereas the vibratory motion requires smaller energy, hence the wave numbers are 300 to 4000 centimeter minus 1, and the rotatory motion requires least amount of energy, it takes about 1 to 300 centimeter minus 1 wave numbers. We will see in the monitor a diagram. On the y axis of it is energy. Now, we will have E double dash on this particular one called electronic energy level, which is in the ground state. This E dash is the electronic energy level in the excited state. Both these have got other vibrational levels called 0, 1, 2, and over and above the vibrational level there will be rotational levels. These rotational levels are small lines that are observed on this vibrational level. Like that, there will be a structure of rotation as well as vibration and superimposed on electronic in the ground state as well as in the excited state. In the ground state, in order to get the rotational spectrum, we will have the molecule must have a permanent dipole electric dipole moment, whereas if we have to get a vibrational spectrum, we require a change in the dipole moment that contributes to the vibrational spectrum. Whereas in electronic spectrum, we will have both rotational fine structure as well as vibrational coarse structure, both are observed. Hence, we will try to concentrate on vibrational coarse structure in this particular lesson. The total energy associated with the molecule is E t is equal to E electronic plus the vibrational part of it we are dropping because of very low energy, the rotational part we are dropping. Here V is the vibrational quantum number, nu E is the wave number associated with the electronic part of it, and this part, first part is called the harmonic part of the equation. We have to introduce anharmonicity also in this, which makes the equation V plus half to be square quadratic, and nu E bar and x e is anharmonicity constant. for greater and much more greater accuracy, we will introduce other types of constants. So, the equation will turn out to be like this. The vibrational core structure of electronic absorption from the ground state to the excited state is shown in this particular chart. Here we will observe E double dash, that is ground state, electronic, and these are vibrational levels. Vibrational level V double dash is equal to 0, it starts and it goes to V double dash is equal to 0, V single dash is equal to 0, that is the excited one in the upper electronic state. So, this is a transition, this transition shows this particular spectral line. Hence, this spectral line is given a name 0 0. Similarly, this when it is going to 1 in the excited state is a transition called 0 1. Similarly, we will have 2 0, 3 0, 4 0, 5 0, 6 0. So, these are all set of lines, and these excited energy levels are all coming closer as it goes to higher, because the energy associated with the bond is weaker as it goes to excited level. Consequently, the spectral lines also come closer at this particular one. So, as it is progressing, we will call it as a progression. So, this progression is called V dash progression. Associated wave numbers are given in the form of this equation nu V dash V double dash with the help of this change in the electronic levels and change in the vibrational levels of the lower as well as upper. Now, this equation tells us the 0 0 transition, the wave number, that is given by E dash electronic excited minus E double dash electronic ground state, and the associated constants, the vibrational wave number V e dash bar and X e is the anharmonicity constant of the upper electronic state, and X e double dash is the anharmonicity constant of the lower state. In this chart, we will be observing on x axis internuclear distance and y axis the potential energy associated with the molecule. Here, this is the Morse curve of the potential energy of the lower or ground electronic state, and this is the Morse curve of the molecule in the upper electronic state. Lower electronic state, lower vibrational state and upper vibrational state. Again, upper electronic state have these two vibrational states. Here we will be taking the E double dash 0 as 0 point energy of the molecule. Hence, this particular height is supposed to be a distance or associated potential energy which is sufficient for the atoms to get dissociated and molecule does not exist later. The vibrational term value energy is given as E v, that is equal to this E v, and we will have V plus half into nu e bar minus V plus half whole square into nu e bar plus x e plus the cubic part of it, and in this equation will turn out to be E associated with that 0 point energy, giving you the vibrational energy of the modified system as half nu e bar minus 1/4 nu e bar x e plus 1/8 nu e bar and y e. The energy associated with the modified vibrational level E 0 V is now given in this form as V into nu e bar V square into x e nu e bar minus V into x e nu e bar plus V cube y e nu e plus 3 by 2 V square y e nu e plus 3 by 4 V nu e y e nu e, and this can be written by separating the terms of V, V square and V cube in this particular fashion. Now, this is equal to this particular part, we will call it as equation 6, where this nu 0 bar is equal to these terms which are there in the first part, and this x 0 nu 0 bar is equal to these terms which are in the second part of it, and y 0 nu 0 is equal to this part which is in the third one. We give these things equation number 7, 8 and 9. Now, we will have a wave number associated with V dash and V double dash. So, nu bar, that is equal to the 0 0 component of it plus the remaining components all can be grouped into E 0 dash V dash minus E 0 double dash into V dash. Now, what we have just now discussed as delta E, that is the first differences, is equivalent to nu 0 bar minus nu 0 bar x 0 minus 2 x 0 nu 0 bar and V. This is our 11th equation giving us the first difference. After the first difference, we will take the difference of the difference, that is called a second difference, delta square E V plus 1, that is pertaining to delta E V plus 1 and half minus delta E V plus half. So, this is called second difference. Now, the second difference turns out to be, after substitution of the suitable equations, we will get it equal to minus 2 x 0 nu 0 bar. Now, you observe the equations 7 giving nu 0, 8 giving x 0 nu 0 bar, 9 giving y 0 nu 0 bar, and 11 is the first difference, 12th is the second difference. Using all these 5 equations, we will be able to get the values of x e nu e of the ground state as well as x e nu e of the upper electronic state. We will try a particular application of what all we have done in the theory. That particular one is, this is a model of aluminum burnt in air taking oxygen will give us a molecule called ALO. This ALO molecule and its spectrum we are going to study to evaluate the ground state as well as excited state constants. Now, I will try to show a somewhat similar experimental setup that can be used to take aluminum band spectrum. Here I have kept 2 iron rods. These are the 2 iron rods. These 2 rods are brought so near, and the upper one is connected, for example, to positive of a power supply, lower one is connected to, for example, negative of a power supply. When the power supply is sufficiently high, suitable to produce a spark between these 2, and this will provide a spark spectrum of iron that is coming through the collimator into the grating and falls into the telescope, and here instead of the eyepiece we can keep a camera loaded with suitable either a film or a particular photographic plate. Such camera on which if it is recorded, you will be getting the iron arc spectrum. This is the iron arc spectrum. Such arrangement is made to get an iron arc spectrum. The iron arc spectrum that we were talking is recorded at the, for example, top of this particular film. Again, a similar iron arc spectrum is recorded at the bottom of that particular film. Now, in between these 2, we will have what is called aluminum band spectrum. Now, we will have, instead of iron rods there, we will keep aluminum rods, two aluminum rods, one above and one below, similar to earlier iron rods, are kept, and the power supply is given to the upper one as positive, say for example, lower one as negative, and this produces a spark between two aluminum rods. This spark contains aluminum takes oxygen from the air and provide that ALO bands, and this spectrum will come through this collimator and grating and into the telescope and ultimately to the camera. The one that you have earlier seen in this particular film is in the middle part of it. This is the aluminum spectrum. Aluminum spectrum consists of bands, first band, second band, third band, like that. Iron spectrum consists of only lines. Iron is a standard one with which aluminum lines are compared, and through the comparator we will try to find out the wavelengths of the aluminum lines. We are going to see that in the next chart. Now, we have a set of wave numbers associated with the wavelengths of the film that we have seen earlier. All these are wave numbers given in this column, and we have got vibrational quantum numbers associated with the V dash and V double dash. All these are those things that are associated. Now, we have to use this data and find out the frequency and the anharmonic constant of the lower or ground electronic state as well as the upper or excited electronic state. This is the De-Lander table of aluminum system, ALO system, and in this we will observe V dash is the column wise, V double dash is the row wise. Now, V dash 0, V double dash 0 is called 0 wave number, that value is this. V dash 1 and V double dash 0 is this particular number. Now, what we do? We will take the difference of these two, get this difference called first difference, and similarly this V double dash 0 and V double dash 1 and V dash 0, we will have these two particular wave numbers, and the difference between these two is this particular number. Similarly, V double dash is increasing to 2 and V dash is having the same from 1, and between these two we will have the difference, and it is written here. These three first differences are taken and they are averaged and kept in this particular column. This is delta E V dash first difference. Now, in the same way we will have this particular second set. We will have the first difference here, similarly next first difference here, next first difference here, next first difference here. All these first differences are taken and they are averaged and kept here. Now, in the same way we will have these two are taken and the first difference written, these two are taken and first difference is written, like that another first difference that is available here. These three first differences are averaged and kept in this particular one. Like that we will have all the first differences of this side and kept in this particular column. They are all given as delta E V dashed, and all these things are taken and take the average of them. Now, we will try to find out the delta V E V single dashed. This particular thing can be obtained by taking the difference between this wave number and this wave number. We will have this number. Similarly, this wave number and this wave number, we will have this difference. Similarly, these two and we will have this difference. Average of all these things is written here. Similarly, average of all these 4 is taken here. Similarly, average of all these are taken here. Like that, we will have averages wherever we are getting are taken here. Now, the average of entire of all these things is also taken. This column, that average we will get as delta E V dash, and this row average we will get as delta E V double dash. So, once that is understood, we will take the second difference. This is the first difference average of this column, and this is another column, and between these two, if you take the difference, this is called the second difference. Similarly, this particular thing is the second difference of this particular thing is the second difference of these two, this particular thing is the second difference of these two, this particular thing is the second difference of these two, and all these second differences put together, it is called delta square second difference E V double dashed. Now, we will have the similar second differences on this side. Second difference is delta square E V dashed, and similarly second differences are all taken and the average of it is taken. The earlier Delander table that we have seen has been formed, and using that we have taken first difference and second difference. Now, this is the first difference, these values that we have seen already. This is the second difference, these values also we have seen already. We will use these values and evaluate the molecular constants. We have seen the values of first differences and second differences, and now they are associated with the earlier equations we have developed, equation 11, 7 and 8, equation 13 and 8. We will put these values in this and substitute these values, and we will try to get the delta to E value, and from this we will get the solving these equations, we will get the value of nu E dashed bar and x E dashed. This is excited, dash means excited state. This is anharmonicity constant, this is the wave number and the associated frequency, and we will also get the energy. Similarly, for the ground state, we will get this nu E double dashed bar and x E double dashed. Now, the entire exercise that we have done is to evaluate the frequency of the vibration and to find out to fit in the Morse equation into that and evaluate the constant A, which gives the shape of the Morse curve, potential energy curve. Ultimately, we will end up with the dissociation energy of the molecule. These are the things we get from this analysis.
మా కార్యక్రమాలపై మీ సూచనలు, సలహాలు, అభిప్రాయాలు మాకు తెలియజేయండి. మీ సూచనలు, సలహాలు, అభిప్రాయాలు మాకు తెలియజేయవలసిన చిరునామా: డైరెక్టర్, ఆడియో విజువల్ ప్రొడక్షన్ అండ్ రీసెర్చ్ సెంటర్, డాక్టర్ బిఆర్ అంబేద్కర్ ఓపెన్ యూనివర్సిటీ, ప్రొఫెసర్ జి రామరెడ్డి మార్గ్, రోడ్ నంబర్ 46, జూబ్లీ హిల్స్, హైదరాబాద్ 500033.